Okay, am I audible?
Yes, sir.
Okay, let me just see if it is started to stream or not. Okay, am I audible? Okay, I can see my video and audio. Great. So let's begin. So am I recording? Yes, start recording. Stop streaming. Okay, great. So what am I going to do today will be the last tutorial on differentiation and its application, and we will also try to cover a few topics related to integration, like just to give you a basic idea, so that from the next tutorial session, since we'll be covering integration in more details, it'll be easy for us. So today will be the last. So with the course is structured such that you have 4 weeks for limits and functions, 4 weeks for differentiation, and 4 weeks for integration. So let's go ahead and try and do some more problems that are related to concavity, L-Hopital's rules, approximation using derivatives, and other problems. We would solve some other problems related to the topics that we have seen in the past. Some more interesting problems. Hopefully that will help you to understand integration better, differentiation better, and you would be able to use them for various applications in your questions. So let's begin. So today let's start with what is, I think I had just briefly talked about concavity of functions in previous session. So what did I say is if this is known as concave up, right, and this is concave down, or you can think of it this way. So a concave mirror is something like this. When you look from the side, it's inwards, right? So it's opposite to of what is known as what is convex. So it's bulged inwards. So if you look from down upwards, so you will see. So let me just a moment. So I'll just confirm which is the perspective in which you say concave up and concave down. Okay. So concave, I was if I was wrote this one as down, so and I should write this as down and this is as up. So it means that if you look from up, you would see a concave surface, and if you look from down, that's what I wrote, I believe, I don't remember. So anyways, for if you look from down, you would look a inverted curve. So or you would look at a concave surface if you look from downwards. So this is known as a concave down function. This is a concave up function, or a U-shaped function would be is a function that you would look for. This is also known as a convex function for this reason. So it's concave up or a convex function. For obvious reasons, we would not go into, because any 2 points if you join, it's above the line, above the curve. That's why it's known as a convex function, and this is known as a concave function or concave down function. So if you just want to write concave, this is concave and this is convex, and so if you want to mention which side you're looking at, so you can look from down or up. So a curve facing downwards is known as a concave down curve, and this is a concave up curve. Now how do you do it? Using calculus. So how do you understand if a curve is concave or up or convex or concave? So what you do is if the curve is something like this, let's consider a concave up curve for our understanding. So first let's do a geometric interpretation, and then we would do a algebraic way also. So let's think that it is a y equal to now x square curve. So let's look on the right hand side. So you have this point, right? This point. So what do you see? You have a theta and you have theta 2, right? And you see theta 2 greater than theta 1. What does it mean? That thetas are increasing as a function of x, right? What does that imply? What does that suggest? What can theta be written as? Can anyone tell me what is the at theta x, say this is x2 and this is x1. So let's write x2 and this is x1. So what is the relation that theta of x2 will have with theta of x1? So tan theta of, so am I audible? So I don't see any responses today. Tan theta of x2 can be written as
dy by dx at x2.
At
x2.
Similarly, tan theta of x1 can be written as dy by dy dx of x1. So now, if we see for all x2 greater than x1, dy dx 2 is greater than dy dx 1. So what can we say? We can say ddx of dy dx is greater than 0, right? Agreed, right? So this is for all x, these are two functions, right? And if one function is greater than the other, this suggests it's an increasing function. Dy dx is an increasing function. So what does it mean? That ddx of dy dx is greater than 0, right? Any doubts?
No, sir.
So if these two are, if your tangent or your gradients are increasing or your derivative is increasing, it means your second derivative will be greater than 0. We have already seen if fx is increasing, f dash x is greater than 0. Just recall, right? From limits we had seen this definition. So since this is true, so these are also functions. So if your dy dx is some function y, say y dash is equal to dy dx, and this is increasing, so your y double dash is greater than 0 from definition of functions, right? So for a concave up or convex function, you see d2y dx2 is greater than 0, right? Similarly, you can try it as a exercise, d2y dx2 will be less than 0 for a concave down function, okay? Because it's a decreasing function, I guess you understand. You see your tangents are decreasing, right? The slope of the tangents, when it's theta 1 is more negative, theta 2 is less negative, and it finally goes to 0, right? I guess you understand. Okay, so are we ready to go to the next the crucial thing that we had done previously, or we had just touched upon as a point of inflection? So I would again go back to history of calculus and say, what was calculus invented for? It was invented for understanding laws of motion. So when a particle was seen to follow a particular trajectory, we were interested in finding velocities and acceleration of that particle. So that was one of the primary objectives of understanding calculus. So let's see. So this intuition would be very helpful. So you see, you can see this is a concave down curve, right? Or this is a concave function, right? And this is a convex function, agreed? This part is convex and that part is concave. So somewhere in between, so you agree that this part is the second derivative is the convex part is greater than 0 and concave part is less than 0, right?
Yes, sir.
Yes, sir.
So if your upward is less than 0 and your downward is greater than 0, and if your derivatives are continuous, second derivatives are continuous function or second derivatives exist, you agree by intermediate value theorem there would be a 0 of the second derivative. By IVT there exists a C such that d2y dx2 at C is 0, you agree? Because
Yes, sir.
x less than C, dy dx, d2y dx2 is greater than 0 or less than 0, and at x greater than 0, greater than C, d2y dx2 is greater than 0. So it has to be a 0 at C for continuity, right? For continuity, for second derivative to exist. Right? So you have to, we are assuming that for these functions second derivative exists. If it does not exist, we'll have to see first derivative method that we have seen last day, right? And we will see today also. And first derivative changes sign and all, you can see that, right? So you can also visually see this. So your curve, so I'll draw this somewhere here. Let's draw it somewhere here. Inflection. See. Do you observe if this is, I'll also intuit it by giving a, so if this is your xt curve, so it's xt and this is time and this is a particle's position. So do you observe that the particle is from this point, it is going upwards or it is going towards the positive side, right? 0, and this is your positive, this is your negative, right? So it's having a positive velocity. Agreed?
Yes, sir.
So it is going somewhere, its velocity is also increasing in some way. Now, do you also see that the particle somewhat later is going to go backwards? Here your velocity would keep on, here velocity is decreasing, right? Your velocity is going to decrease this side because it's a negative slope, you are going downwards, so you're going in the opposite direction. But somewhere in between, something must have happened, right? So because your velocity was going on increasing, and suddenly after this point, your velocity, what happened to your velocity? It started to decrease, right? Here velocity was increasing. I will show you why. I will show you, and here, but from the graph, from the tangents, it's clear, right? Velocity decreasing. It means that there is a change in acceleration, right? So velocity is decreasing means you are decelerating the particle in some way, in between. So you're in between, your particle must have your d2y dx2 or your acceleration curve must have changed sign, right? So say this point is C1 and this is C2, and you had velocities greater than 0 from C1 to C2, and then finally you went to a negative velocity. So do you agree that to bring this to a negative velocity at this point, or the point of inflection C, it must touch the curve because its velocity is decreasing from this point? Did you?
Yes, sir.
Are you getting this pictorial representation? So are you getting the the particle sense, I think this is a very nice intuition you can have. So from this point, your particle slowly is going to decrease its velocity, which means your acceleration is going to become negative because you'll be pushed towards the opposite direction. This point is your point of inflection. This is your velocity curve, right? I hope you understand. So if you have doubt at this point, please stop me, or I'll go to the I'll solve this more formally. For example, so here I have taken another trajectory. That's what I took there to understand how I took this curve to understand dynamics of acceleration. But here we would take a simpler example. So velocity would be dx dt, and what do you see? X cube is equal to 2x square, right? So what are you seeing? Your velocity is decreasing. As you are going towards 0, your velocity decreases and then it increases. So which means you would have a further, if you do dv dt or d2x dt2, you would have a curve like, or it is 3x square, sorry, 6x, which is, agreed? So at minus infinity, your particle was moving at very high velocity, and suddenly you had a very high negative acceleration, right? Slowly the acceleration was decreasing your velocity. Finally, it sent it to 0, and then it starts to increase. So your acceleration is an increasing function. So you see here also your acceleration changes sign, right? So your acceleration was negative here, and the magnitude of your acceleration kept on decreasing, right? So you see or rather in magnitude it kept on decreasing, or your acceleration as a signed product kept on increasing, because we are taking sign in mathematics. Otherwise you are slowly coming towards your 0. So here you had a very high positive velocity. You are moving towards a very high positive velocity. You had a retardation. Slowly the retardation decreased and brought your velocity to 0. As soon as it brought it to 0, it started again increasing the velocity. And that is, we can see from the AT curve. And now there is a point of inflection at x is equal to 0. So this is a concave function and this is a convex function, clearly from the curve. So you can see here this point d2y dx2 changes sign, right? Agreed?
Yes, sir.
So whenever whenever d2y dx2 changes sign, you would have the understanding that there is an inflection point. That's what I was trying to intuit by this particle sense. So where you have a very high velocity and your acceleration is negative, is slowly decreasing, acceleration negative, the magnitude of acceleration keeps on decreasing, and then it goes to positive, right? Did you understand, Mr. Pandey? So today you are not interacting, so that's why I'm asking. So it's okay, I can't hear you. So whenever you have this type of question, you try to go back to this acceleration example and try to understand, reconcile it with yourself. So let's solve this question. I think this question is a very simple question. So
yes, sir, I know these things.
Yeah, good. So let's look at this. So then we'll go fast. So we'll solve more questions today. So g of x is this. Where are the extremas? So gx is 5 minus 6x minus x square by 2 plus x cube by 3, right? So your g dash x is 6 minus x plus x square, right? Or x minus 3 minus 6, right? Minus 6 and x plus 2, right? Or you have is x is equal to 3 comma minus 2 are point of extremas, right? We're just warming up for the next few tougher questions. So x is equal to 3 comma minus 2 are your extremas. So now you tell me, we can also do a second derivative test and see which is a positive number and which is a negative quantity. But without that, what do you think is which extrema is a maxima and which is a minima? We'll also need to do g double prime x. Let's keep that in hand. So that is minus 1 plus 2x, right? That is g double dash x. So for your extremas, without doing a second derivative test, can you tell me, already, although you have it on your hand, which point is the maximum and which is a minima? This is
Minus 2 is maxima and 3 is minimum.
what logic did you use? So consider this g dash function.
Wavy curve method.
Correct. So I had shown the wavy curve method to you last way. So what you do is this. So above 3, this is positive, right? dy dx is positive. At 3, dy dx it goes to negative, and again minus 3 it goes to positive. We have seen it changes sign. So now at 3, if it is going from negative to positive, right? So negative means if your dy dx is negative, it means it's a decreasing function, and then it's increasing. So 3 is a minima. You said that, right? 3 is a minima.
Yes, sir.
And 2 is a maxima, right? Because its side is positive, so it's an increasing function and then it decreases. So you can also do a second derivative test and see if it is the same. Second part of the question is, this is also your this is not only your wavy curve but also your true curve, right? G dash x, because it's a polynomial. This also looks like this, right? It's not only your like sine curve, a polynomial cutting at 2 and 3, so it's a quadratic, so it will look something like this. Agreed?
Yes, sir.
So your number B says that points of inflection. So we'll put g dash x is equal to 0, right? We have seen d2 by dx2 has to be 0 at points of inflection. Great. So here the point of inflection is 2x minus 1 is equal to 0 or x is equal to half, right? Agreed? Now
Yes, sir.
part C is plot the curve of this function. So how will I plot this curve? So I see that there is a maxima at 3 and a minima at 2, right? Or something like that. Minima at 3 and maxima at minus 2. So I'll plot g of x. Can any one of you help me with it? So what are the points that I need to consider first? So it's a positive, so x tends to positive will be a positive infinity, negative will be negative infinity. That's not a problem, right? G of x is x cubed by 3 plus x squared by 2, or rather minus x squared by 2 plus, or rather minus 6x plus 5, right? So your curve would look something like this, right? So your curve would look at a point of minus 2, you would have some maxima. At a point of where is it, 3, you would have a minima. Let's see which is the maxima and which is the minima, right? So g of minus 2. What is g of minus 2? So I've written this function there. Let me just, so it's minus 8 by 3 minus 2 plus 12 plus 5. Is it correct? 8 divided by 3 minus 2 plus 12 plus 5. So it's 17.
Yes, sir. Correct.
17.67, and g of 3 is it's something like 27 by 3, that is 9, minus 9 by 2 minus 12, or rather minus 18, right? Minus 18 plus 5. So I have 9 minus 4.5 minus 18 plus 5. That is minus 8.5. So you have something here, you have negative, and here you have positive, right? So how many roots do you have for this curve? A quadratic can have one root or no root, right? We all know that every real root occurs in pairs, right? Because if you have to shift, because a n-dimensional graph will have n minus 1 extremas. So if you go to negative, you will have to come up at least once. That's the idea. Right? I'm just using the intermediate value theorem. This is what your curve will look like. I'm not calculating what the 0 is at, but it will be somewhere between minus 2 and 3, right?
Yes, sir.
Minus 2 and 3, your curve will be somewhere in between. Because, and we all know that if this was somewhere here, so your curve would have looked something like this, where you would only have one root, right? So that is the way you go about, because once say you have an extrema, right? And you have another extrema that is in the opposite field, you must cut the curve you must cut x-axis once in a polynomial, because as it's a continuous function and by intermediate value theorem. Similarly, as it goes to infinity and it goes to minus infinity, you should cut it again. So you should at least cut once. It depends upon whether the corresponding, or if you arrange the roots, if your roots are in the opposite hemispheres, you would always have n minus 1 roots. So here any quadratic would have, cubic equation would have 3 roots, right? So in 3 roots, if your extremas are in the opposite direction, so you would have 3 roots, or you would have just 1 root, and you would have the curve something like this. This is what I meant. Okay. So next, I would ask this question, that y is equal to x to the power 2n. So do you have a point of inflection at x to the power 2n? Question 2. Y is equal to x to the power 2n, where n is an integer. Is x is equal to 0 and point of inflection? So n has to be, say, greater than equal to 2, right? Is your even for so it's for all integers, x not is equal to 0. I should have written whole number or natural numbers. X belongs to natural numbers, so let's change. So it's from 1 to. So does that is it a point of inflection? See our definition. So d2y dx2 is 2n into 2n minus 1 x to the power 2 into n minus 1. Agreed? So first derivative is x to the power 2n minus 1, 2n. Second derivative will be 2n minus 2.
Yes, sir.
So is this 0 at x is equal to 0?
Yes.
So do you think it's a point of inflection? So by whatever we have seen, it should be a point of inflection. But let's see. Your y to the power x to the power 2n looks something like this, right?
Yes.
And even your y, this function, some proportional to x to the power 2n minus 1, that is also an integer, or at least it will be x1. Agreed? It will be 1 or 1, like x to the power 2k again. K belongs to whole numbers, right? So that is also either this or some constant. That is, if you are for x square function, then your x to the two derivatives would give me 2x, 2, just 2. It is either 2 or a upward opening convex function. Now does your g double dash or f whatever you function you have, d2y dx2 function, cross the x-axis? So it always remains positive. So there is no point of inflection. You only have a horizontal tangent. So at x equal to 0, d2y dx2 less than x minus is also greater than 0, and d2y dx2 at x plus is also greater than 0. Therefore x is equal to 0 is not an inflection. So always remember, if you are confused, inflection points are those where your acceleration changes sign, right? So either you are accelerating, you go to retardation, or you are retarding, you go to an acceleration. Agreed?
Yes, sir.
I think this intuition, if you follow, you can always do it. So in general cases this will always be true, but in some special cases you can see that it cannot hold true as well. So if x belongs to point of inflection, then d2y dx2 at x is 0. Reverse is not true. So it's a if only statement, not if and only if. So this is important. I hope you got the message. So this was just to convey this message. So now we would do something known as a approximation of derivatives. So why are we doing derivatives? We had told in the first class that it was an approximation of the slope. When I introduced derivatives, I told in a straight line that theta was just perpendicular by base. You take any x plus delta, right? F of x plus delta, it would hold. But in our case, we divided the problem. That was the heart of calculus. We divided the problems into smaller sub problems, so that for any arbitrary class, this would be exactly a triangle, right? Right angle triangle, or the tangent at the curve. Remember that? I hope you remember. This was the first thing we did in derivatives. Now, if we are to approximate, look at this curve. If you are to approximate, say this function, right, f of a plus delta x. So how can you do that? So that's what we will be seeing. So you consider this graph here. What do you see? You see, if I take a derivative at this is a tangent like this, right? Now I go delta towards the right. If you want me to draw again, please tell me, or else I'll just draw here because it's easier. Now what happens is, can you see this triangle, right? This triangle is nothing but, if I name this df by delta x, would be same as the derivative of the curved line at x is equal to a. Agreed? Or f dash a. Is it correct?
Yes, sir.
And this is known as the differential. Or how much is your y changing in your derivative form? It's not the actual change in y, right? Remember that. So this is your y changed, y final, sort of. When you added delta and found the actual value for that, right? So now you can see what is the differential change in your x by just multiplying, since this left hand side is a fraction, right hand side is a derivative. So fractions can be opened up, right? So you can just multiply delta x and you get the differential of what is the increase by just doing this. I just moved it towards this side. Agreed? I hope it's clear. Now your delta, or this is also known as the error. So this I'll call as error. So you are using your derivative to approximate the next point. This is also known as an Euler method. I don't know if you have heard it. So people draw curves by using a differential equation. I'll show you how to do that today. But let's do this thing first. This is also known as an Euler method. So you would, if you would follow this tangent to get the next point in the curve, so you would be falling short in case it's a concave upward function, and you would overshoot if it was a concave downward function. Do you see that? You're overshooting, right? In this case.
Sir, please repeat last point that you say.
Yeah. So let's draw it again and see. This is also known as the Euler method. Euler, Rangakata, many methods are there to just plot graphs. So if I give you an x0, y0, right? And I give you dy dx, right? So say this is x0, y0, and you say this is your original curve, your y curve, but you are only given dy dx at x is equal to 0, right?
Yes.
So I'll do two cases and then it will be very clear. See, now if I take the I use the tangent, right? I want to find x1, y1 as the next point on the curve. It's a sort of inverse differentiation problem. So you can see, if I consider this triangle, right, and this is your x0, right, and I move some delta, x0 plus delta, right?
Yes.
So what is this? This is delta, you agree?
Yes, sir.
And this is dy dx into delta.
Yes, sir.
Because delta is your dy dx is tan theta, right?
Yes.
So tan theta into your base is your perpendicular, right?
Yes, sir.
So your x1 is x0 plus delta, y1 is y0 plus dy dx at x0, y0
X0, Y0
into
into
delta.
delta.
But you see something here, there is a problem. So you finer you choose your delta, this delta, capital delta, you see your curve will look better, right? Or if you follow this method like this, your curve will look like something like this. It will not look bad, but it will look like broken lines, right? If you use quotes. Agreed?
Yes, sir.
Because you're just taking lines, you're taking line segments to approximate a curve. Now, if I was this side of the curve, the Euler method would shoot me off, right? So this is your x plus delta. This is dy dx into delta, right? So let's take the x prime 0 and y prime 0, right? So you would overshoot the curve. Agreed?
Yes, sir.
And then this would be your error. Your error can be either negative or positive. So your error is defined as and I am writing this as delta, is defined as, how will you define? Actual value of the function at x plus delta, right? Minus your
Fx0.
df of x0, y0, right?
Yes, sir.
This is your df. We have defined this as df as x0, y0, or the differential. So in case it's a concave function or looking convex function, this will be positive, right? Your curve is above the tangent. And in case your curve is lower than the tangent, your differential value will be greater compared to your function value. So it will be negative. Agreed?
Yes, sir.
So this is a very important method. So this is one of the beginning things you do in differential equations and also in computational computer science, where you try to use numerical methods to plot graphs. You may not have your like in Schrodinger's equation, in many like heat equations, in your Maxwell's equations, you don't have the closed form solution always. You just use the differential equations and use the Euler's method to plot the curve. Right? We can use this as an approximation. Agreed? Whenever you have differential equations at hand, if you have the derivatives and at the starting point, you can always plot a curve, right? You can approximate your original curve. This is my idea. So let's see. This is what I told below. Now let's solve this question. Now we come to the interesting part of the session today. Fx is equal to root over of 26. So how do I do this? Any idea?
-27 -1.
Yeah, that I understand. So I just explained this thing. So what did I do? So you see, root 27 is 3, right? We know this. Now how do I do this? So to do this, we have seen delta is equal to delta y minus df, right? This is the error. Agreed? Now let us consider, let us assume, because delta is very difficult to compute, delta tends to 0. For small delta is small, right? But not tends to 0 is small, right? Compared to other values. So we'll ignore this for the time being. So your delta y can be also your differential and approximation, right? This is what I was coming to, or in other words, df delta x is your df dx or dy dx. So Ravi, we are discussing the topic we are discussing is derivatives. Last session of derivatives. Please join on 9. If you and we discussed concavity. We have solved problems related to that. We have solved problems. Now we are discussing approximation using derivatives. So next, so we would also do a lot of L-Hopital's rule and beginning of integration. So let's see. So this is an approximation, I assume, right? So if you see you d of x df or your delta y, I can write this as dy dx or approximate it as at x, or we'll see delta x, right? So basically I am saying I am approximating this ratio as a derivative. This is more intuitive to remember, right? Understood? If you don't know, if you have a doubt, you do the next step. If you don't have a doubt, you just tell me what would be the next step. What should I do next? So I have a function f of x is equal to x to the power 1 by 3. What should I do next? And I am told to find f of 26. How do I find it? No answers? So what Mr. Pandey said is, I can write it as 27 plus delta. So this is your x naught plus delta is equal to 26. So your delta is equal to minus 1. Agreed? So I know f of 27 is 3. This is why I am using 27, right? And it's close to 26. That's why I am using it. Okay? So I see no responses. So dy dx.
Find dy by dx.
would be 1 by 3 x to the power minus 2 by 3, right? Agreed? This is dy dx, and I put x is equal to, what will I put?
27.
Correct.
X is equal to 3.
27. We took x naught is 27, right? Why will we put 3?
क्या कहते हैं?
So it's minus 2 by 3, 27, right? So we're just putting x naught comma y naught. X naught is your 27, y naught is your 3, right? I have already shown this method before in the Euler. This is an Euler method. So this is 1 by 3 into 1 by 3 square, or 1 by 27, right? Agreed?
Yes, sir.
27 comma y naught is 3. What is your delta x? Minus 1. And delta y is your, you can approximate delta y as, what is delta y? 26 plus delta minus f of 20, or 27 plus delta minus f of 27, right? This is your delta y.
Yes, sir.
We defined this before. So dy dx we have found to be 1 by 27, and delta x is minus 1. So I see f of 27 plus delta is equal to f of 27 minus 1 by 27, and delta is equal to minus 1. So I get f of 26 is equal to f of 27, which is 3, minus 1 by 27, right? So this gives me what, let me see what is this value. 3 minus 1 divided by 27, this is 2.9629, it says. And what is the real value of this? Is f tilde, let us write, right? Let's write f tilde. So actual f26, let me see what is the value in the seeing it in the calculator. 26 is 2.9624. Isn't it a good approximation? Without using, these were very helpful in the days of calculator, when calculators were not there. Now also, if you cannot calculate a particular function, often differential equations are easier to calculate. Did you get the crux of this problems, like this type of questions, how to solve them?
Yes, sir. Clear.
Okay. So now the last thing, I think we did this in school, but maybe I'll just give you a basic idea. So what is the idea is of the theorem of the L-Hopital's rule? It says that if your function is, we have done so far limits without using L-Hopital's rule. So fx by gx exists, and both your limits are either 0 or infinity. So f by g is a infinity by infinity form or a 0 by 0 form, because 0 by 0 and infinity by infinity are the same, right? So you can just take 1 by infinity is 0 by 0, right? This is your infinity by infinity form. So you would agree that 1 by gx and into 1 by fx is 0 by 0 form, which is same.
Yes, sir.
So your infinity form, 0 by 0 form are essentially the same thing. So if your function is differentiable at all these points, so what you can do is differentiable at all points except at point of A. You need not be differentiable, but if it is differentiable, you can just, it is that does not solve the purpose of limits. If it is differentiable in all points around A, so you can use derivatives. I'll give you a hand wavy proof. The actual proof, like the proper theoretical proof, is in the tutorial, in the lectures of this course. It's not useful to give that proof again. So what I do is, you agree that f of x minus f of a at x tends to a would be 0, right? Or would also be, I can write f of x as, why did I write f of x by f of, so f of x f of a I am telling tending to 0, right? So if I subtract f of a from f of a, so you agree that, and f of a is 0 for your information. F of a is 0. I can always subtract that, right? I can always subtract 0 from the numerator. That's what I have done. So I have subtracted f of x minus f of a, which is equal to 0. Agreed?
Yes, sir.
This is also equal to 0, and then I have divided by x minus a. And I have set limit x tends to a. If I do that, it's nothing but the derivative of the numerator and denominator if they exist. Right? X minus a is also, I can do that, right? I have divided both numerator and denominator by x minus a. Agreed? So that's
Yes,
why
sir.
this numerator is f prime a and this denominator is g prime a. So let's solve some questions. We'll try and finish up fast. So question 4, we have a lot of questions to solve. So limit x tends to pi by 2 minus cos of 3x by cos of 7x, right? So you agree that cos 3x by 2 and 7x by 2 are all 0. It's 7 pi by 2, right? Not x by 2. These are 0.
Yes, sir.
So cos is 0 at all, or it's 0 at 90 degree, 270 degree. So it's 0 at 2n plus 1 pi by 2, right? 0. So what can I do using the L-Hopital's rule? Just put 3 outside, cos of 3x, cos of sine of 3x, sine of 7x, right? Agreed? Now sine of 3 pi by 2 is, so this is your, I can put 3 by 7
Minus
outside.
1.
Yeah, I'll do that. That's why I was saying pi by 2 sine, I'll just write 3 pi by 2 sine 3 pi by 2 by sine 7 pi by 2. So 3 pi by 2 is a bit more than pi, right? So all sine, tan, cos. So in this coordinate, sine is negative. So 3 pi by 2 is pi by 2 into 3 or minus 2 or 270 degree, where sine is negative. It's minus 1. Where what is 7 pi by 2? So your 4 pi by 2 or 6 pi by 2, right? 6 pi by 2, you agree, is equal to 3 pi, right? So you complete 2 pi and you come back again 3 pi and you add pi by 2. It's again minus 1, right? Do not make any mistake, right? 7 pi by 2 is 2 pi, 3 pi, 3 pi plus pi by 2. 7 pi by 2 is 3 pi plus pi by 2. Agreed? So 3 pi is aligned with 180 degree and plus pi by 2 is 270 degree, right? If you have a different calculation, please stop me if I have made a mistake. Answer matched, right? Limit x tends to 0. So if you are not seeing, let me just check. Sine 7 pi by 2. Yeah, correct. Great. So tan of tan x by sine of sine x. It's a 0 by 0 form at x is equal to 0. Tan x is 0. Right? Sine 0 is 0. So we can use L-Hopital's rule again. So what is the numerator? Sec square x, or here you use the chain rule, into sec square x, right? Correct?
Yes, sir.
The denominator is sine cos of sine x into cos x, right? Using L-Hopital's using chain rule and L-Hopital's rule, I differentiated these two. So the numerator becomes, so tan x is 0, so sec square 0 is 1, right? Cos and sec at 0 is 1, 1 into 1 by 1 into 1, which is 1, right? I think we are correct. Good to go, right? We'll do few more L-Hopital's rule question before going into more complicated questions. Let's do question number 5. So question number 5 says that L is equal to limit x tends to 0 tan x minus x by, now to make it more interactive, I'll solve this once you people have solved this question. So I'll wait for 1 minute, wait for you to solve this question, and then I'll solve. Once you're done, just maybe write down the solution, or write the answer, or tell me done, and then we can go ahead. I'll wait till 7:09. Is anyone trying?
Yes, sir. Trying.
Yeah. Wait for 1 more minute, or a couple of more minutes. One by 3. Let's see. So, Mr. Pandit, tell me, what did you do? So, this today will give you opportunities in case who is able to solve, they can prompt the answers. So, what did I do? So, numerator becomes
Sec square x minus 1 upon 3x square.
Okay, next, what did you do?
Sir, again 0 by 0 form.
This is also 0 by 0 form. Now, this is why I wanted to see, this is why you are requiring more time. You are blindly differentiating. See, you don't even need to differentiate this again. Why? What is sec square x minus 1? You remember 1 plus tan square x is equal to sec square x, right?
Yes, sir.
So, sec square x minus 1 is tan square x.
Yes, sir. 1 by 3.
Yes. So, tan x by x is, we know by as sin x by x is 1, limit x tends to 0. So, dividing by cos does not make any difference, right? Numerator, denominator you can divide by cos. So, your limit tan x by cos theta, which is also 1, is also equal to 1, right? Agreed? So tan x by x is also 1. This is what I meant. Since sin x by x is 1, cos is 1 at 0. So your tan x by x is 1. So this is the quicker one. So let's do next question. Next question is very simple. I'll just do it here only. So what should be the answer? Instantly you should answer this. Yeah, Ravi. So I will differentiate the numerator and denominator. I'll get, and we have already seen e to the power x minus x by x is 1, right? So it's half. Correct. So it's instant solution. Next is this. I'll again wait for a couple of minutes. I'll start solving it at 7:13. So I'll copy the question once again and you can try. Let's copy both this question and I'll start solving it at 7:13, 7:14 around. Both these questions. Any progress? Which one is half? 3 or 4? Okay, 3. Understood. Now tell me, what will I do? So L is also equal to, unmute and tell me.
It's cos x.
Yeah, cos x. I differentiate the numerator.
Plus x in bracket minus sin x.
So I'll put minus sin x.
Minus 1 upon 1 plus x.
Okay.
And in denominator 2x.
So it's a 0 by 0 form again.
0 by 0 form, yes. So we'll again differentiate.
Or we can do, yes, we have to differentiate because its numerator is 1, this is also 1, right? And this is 0.
Yes.
It's also again 0 by 0. This is 1, this is 0. So you differentiate again and what do you get?
Minus sin x. Minus sin x.
Right.
Minus x cos x.
Right. Because we're doing the UV rule here.
Yes.
Then
and plus 1 upon 1 plus x whole square.
Correct.
Divide by 2.
So let's put the values now. Now it's not a 0 by 0 form. Denominator is a real number.
Yes.
So this is 0, this is 0, this is also 0.
0.
This is 1.
This is 1.
So you get half. Good. This is what we like. We like a interactive sort of a thing. This is easy also. So number 6, let's try now. Ravi, why don't you give a try? Both of them have given a try. If you want. We are not audible, but if you can sort of tell me what you do. Yes, you can like suggest what solution should we try in this. So you see it's a 1 plus 0 to the power infinity form. We had already seen this once, right? So we'll not do exactly by that thing. So let's stick to our. So we had seen 1 plus 0 to the power infinity. We had seen it to be sin x by, I can do it in one line, right? If you remember my first few sessions, right hand side, I don't know, this is L. So L in one line I had said it is equal to limit x tends to 0 or whatever you have, in this case 0, fx by gx. Remember, if this is your gx and this is your fx. This is one way, but we'll do also using L-Hopitals. No, don't worry. So in case of 1 plus 0 to the power infinity, I said that if it is 1 plus 0 to the power infinity, it's either going towards infinity because it's like slightly greater than 0, or going to some constant number, or it's going towards negative infinity towards 0 if it is slightly less than 0. So let's see. So limit x tends to 0. So let's just solve this limit first. So you have by x and you have a sine bx, right? So I divide by b, multiply by b. So this is sine a by b, sine b, sine x by x form. This is also equal to 1. So I get e to the power ab, right, as L. Do you remember this method, or this is a standard derivative, standard formula? But let's see.
Yes, sir.
Yeah. So now let's see L. So I take log on both sides is another way to do it. So I think Ravi was suggesting take log on both sides, or something like that. I don't know. So let's take log. So if log is, let's assume that the derivative exists or it's a continuous function. It is a continuous function. So I get 1 by x log of cos x plus a sine bx, right? Right? Now you see this is 1 and this is 0. So log 1 is 0. So it's a 0 by 0 form again. So I can take derivative again, right? So it's 1 by cos x plus a sine bx, and numerator will be, if you are following, minus sine x plus ab cos x, right? By 1. This is 1 and this is ab, right? Because this is 0, this is 1, this is 0. This is equal to ab. Log of limit is ab, so L is equal to ab, e to the power ab. Okay, clear?
Yes, sir.
Now let's go to the more interesting problems of today's session. Let's do this question. So this is a tricky one. Let's hear some ideas and then I'll start. I took some time to solve this as well because you generally do not know the path that you should take to solve this. You can go in multiple directions and may not come up with a solution. Yeah. Any ideas? How can you prove? So it's a first class sort of a problem, but you need to be a bit intelligent and solve. So how do you do this? I would begin to solve this, but I want some ideas. Okay, I see no ideas. So one way is to directly differentiate. Way 1. Directly differentiate and make y subject, dy dx subject. But I think this won't work. Very lengthy. You would not be able to separate. So what I did is, another way is, let's try to separate the variables as Ravi is suggesting. So 1 plus y is equal to minus y 1 plus x, right? So I will square both sides. So you have x square 1 plus y equal to y square 1 plus x, right? Or you have x square minus y square, or I'll put y as the subject, so I need to put y square minus x square, or rather let's put y again, y square minus x square y, x square y. So I have put this, and then I'll put, so the y square x,
So write y square by 1 plus y is equal to x square by 1 plus x.
So I know I'll just try to do something like this. I'll show you what I'm trying to do. So it's
Okay.
So that will not work actually. I tried that. Y square x, x square plus x square y, right? This will give me y square, or rather this will remain y square into 1 plus x. This is going to be the same, minus x square y minus x square, right? This will be equal to 0. Understood? Now I can solve for y, right? From the Sridharacharya formula, I would get a variable separated form, right?
Yes, sir.
So I'll get x square plus minus x to the power 4 minus 2 into x square 1 plus x. 4b square minus 4ab. I think I made, let's see, specifically it will become,
Sir, plus 4x square.
4x square will come.
Plus 4x.
yeah, that is okay.
Yes, sir. Square root.
So by 2 1 plus x, I think, let's see, this is the denominator 2a, this is your the other part of y, so y into x square is there, right? So did I copy correctly? I don't know. Let's see. So x square plus minus, so you would have x to the power 4 plus 4x squared plus, it is correct only, x cube plus 4x square, right? So what can I do now? I can factor out x square, right? So I'll get x, and I'll get x square plus 4x plus 4, right? 2 into x plus 1. Agreed? X
Yes,
square
sir.
plus minus, this is x plus 2 whole square. That also you agree? This is x into x plus 2. Right? So now your equation was a one variable, it was not a quadratic, but I made it a quadratic, so I got two equations, but both of these will not be a solution. Let's see why. See, y is equal to x square plus, this is solution 1, plus x plus 2 by 2 into x plus 1. So I'll get 2 into x plus 1 by x plus 1. Assuming x is not equal to minus 1, I can cancel them and I get y equal to x, right? Agreed? This is one solution you get. But you put it in the original equation, you get x into 1 plus x into 1 plus x equal to 0, which is x into root over of 1 plus x is equal to 0, which is true only for x is equal to 1 and 0. It's not true for all x. Not true for all x, right? Therefore, y is equal to x is not equal to x, right? Did you understand the reasoning?
Yes, sir.
So,
Yes, sir.
it has to be true for all y equal to x. So, next is y is equal to, so if you take the negative, x square minus 2x by 2 into x plus 1. This is equal to minus x by x plus 1, right? Now you take the derivative and tell me what is the derivative. You see, the numerator will become x plus 1 minus the derivative of the denominator is x plus 1 minus x by x plus 1 squared. So it's minus 1 by 1 plus x squared. So this is matching, plus you can put this into the equation, right? So the equation was root over of this plus x into 1 plus y is equal to 0, right? Put y, this value here, what do you get? What do you get? Minus x by 1 plus x root over of 1 plus x plus x into 1 minus x by 1 plus x, right? Which is minus x by root over 1 plus x plus x by root over 1 plus x. True for all x?
Yes, sir.
So this is your solution of y and this is your dy dx. So this is, you could have this, until and unless you get this thing, you would not be able to get the answer very quickly. You would have to solve a long question. Now today's moment of the day is be this problem where g of x is, I would copy this question and let's see. This would also give you the understanding of how powerful calculus is. For it can give you idea about any arbitrary function. So this f is not defined right here, but I would be able to comment on the local minima, maxima and monotonicity of the curve. So what is said? G of x is 2 times f of x square by 2, 6 of 6 minus x square, right? In the previous question, why did we reject the one solution? I told you, right? So if first solution y equal to x is not equal to 0, right? You get x into 1 plus x is equal to 0. Is it true? Not true, right? It's only true for x is equal to minus 1 and 0, but it has to be true for all x and y. Understood? That's an equation. Equation must be valid for all. You're not told to solve. Anyways, so for this question, let's go. So let's do this way. So it said that f double dash x is greater than 0. What does it mean? Your function is concave up.
Concave up.
Or a convex function. But let's see how will we use it. What is the idea you say? So your first question is monotonicity. So for monotonicity, what should I do? I have been doing this type of questions for a long time. Now you guys should tell me. Like what should be my step to do comment on monotonicity?
You will find g dash x, and
Correct.
if g dash x is positive, then strictly increasing, and otherwise it's strictly decreasing.
Correct. So I will have to take the derivative. So it's 2x into f square by this into 6 minus x square, right? Into 2x or minus this, right? 2x f dash x square by 2. I'm just using the chain rule. Right? Is this okay? This is g dash x. Now as Hedvi was pointing to me, g dash x is greater than 0. If it is g dash x is greater than 0, then for x belongs to D, so D is the increasing set. So for a concave up function, it will not be monotonic. You can say directly, right? Because your second derivative is greater than 0. This means you will must have a decreased part and an increased part. Let's see. So now let's take x greater than 0. Or let's look at something. Now can you tell me that when will be x, this will be greater than 0? For let's take case where x is greater than 0. Now you will have to see that f dash x by 2 is greater than f dash 6 minus x square. For this to be, if g dash x has to be greater than 0. Agreed?
Yes, sir.
This has to be greater than 0. This has to be greater than 0 if this is greater than 0, and less than 0 if that is less than 0.
Yes, sir.
So now where will it be greater than 0? Tell me. What information do I have in this question that will help me to solve this question? Can you find a very stark definition? like a definition that is given just for commenting on this positivity. Any idea? I will give you a hint. Look at G double or F double dash X. Look at F double dash X. What is it said? It is said it is greater than 0, right? Agreed? What can you infer from this? Mr. Pandya,
F dash S is increasing.
correct. F dash X is increasing. But minima, what? How will I get the value of X for which this is true? Now F dash S is increasing means this will be greater only when x square by 2 is greater than 6 minus x square, right?
6 minus. Yes, sir.
So this is the type, this is why how you will use calculus. This is why calculus is so great. So you'll get 3x square by 2. You don't need f. You just need the property of the functions that the calculus will give you. So x has to be greater than, mod x has to be greater than 2, right? X square has to be greater than 4, which means mod x has to be greater than 2. Agreed?
Yes, sir.
Which means for x greater than 0, for x greater than 0, x belongs to 2 to infinity. Agreed?
Yes, sir.
Case x less than 0, in this case your f dash x square by 2 has to be less than f dash 6 minus x square. If this is less than 0, this also has to be less than 0 for f dash x to be positive. Agreed?
Yes, sir.
So this will give me x less than minus 2. Agreed?
Yes, sir.
So x would belong to minus infinity to 2.
Minus 2.
Sorry. So for x is, so gx is increasing from x belongs to minus infinity to minus 2 union 2 to am I right? I think so. And decreasing for
Minus 2 to 2 open bracket.
no, sorry, I am wrong, because at x is equal to 0 also you will have a change in sign, right? Let's look at this curve. Wait, let's consider this function. Let's say h of x is equal to x square by 2 minus x square. Now this is, at this point we are right. Now we also have a root at x is equal to 0, right? So g dash x plot we should write, we should plot it. So g dash x, let's plot it, then we'll be not confused. So g dash x is 2x into f dash x square by 2 minus f dash 6 minus x square, right? Agreed? What are the roots of this inner function? So let's solve for the roots. So roots are 2 and 2, you agree? 2 and minus 2. Because f x square by 2 is equal to f of 6 minus x square if x square by 2 is equal to 6 minus x square, right? Okay. Now if you have a doubt, please ask. I think you have doubt. So are you getting that I'm trying to plot the wavy curve function for g dash x? This is what I am trying to do. I have seen for x greater than 0, this inner function is positive. And for x less than this inner function is negative. This much we have seen, right?
Yes, sir.
So we have seen this is positive because at 2 you have 0, right? And in minus 2 you have also 0. X is equal to 2 you have a 0 and x is equal to minus 2 you have a 0. And less than minus 2 it is decreasing. Or rather, it's increasing, right? Less than minus 2 it's increasing, greater than 2 it's also increasing, agreed?
Yes, sir.
So you would, from 0 you would increase and you would increase to 0, agreed?
Yes, sir.
And there is a root at 0 also, right? So by wavy curve, this will be your curve. Right? At x is equal to 0, you will change sign, right?
Yes, sir.
So now tell me, which are the points of, or where is your curve max? Now tell me, like x belongs to minus 2 to 0, union 2 to infinity would be the increasing part. Because we are not considering f this function only, we are also considering f dash x square by 2 minus f dash of 6 minus x square, right? Into x we are considering. This is the function we are considering, right? Not only this. Did you understand where did we go wrong? We were just considering this in the previous example. So you were getting minus infinity to minus 2 and 2 to infinity. But you're also multiplying that with x, right? So this is positive here and here it is positive, right? G dash x. Okay. I would like to think you don't have a doubt. And x belongs to minus infinity to minus 2 union 0 to 2 would be your decreasing, right? Now the second part of the question says extremas. What are the extremas and what are they? What are the extremas and what are they? Which is a maxima, which is a minima, and which is 0, minus 2 and 2. 0 is a local minima or maxima. From the g dash x curve we have seen, right? Am I audible? Hello?
Yes, sir. G dash x equal to 0. Critical points 0, minus 2 and 2.
Yeah, so at 0 what do you think is it's a maxima or a minima? So HB says it's a minima. This side is positive, right? Left hand side is positive. It's an increasing function on the left hand side. 0 is, what did she write? Let me just see. Which is minima? 0 is a minima. It's an increasing.
Yes.
It's increasing on the left, right? And decreasing on the right. So at 0 you have a maxima, right?
Yes, sir.
Your left side is positive and your right side is negative, which means that your gradient change after 0 you will become decreasing function. Before 0 you are increasing. At 0 it's the maximum, right? Similarly minus 2 would be minima, right? From negative to positive.
Yes, sir. Yes, sir. Minima. And 2 will be also minima.
Yes, because you're going from negative. So this side is a decreasing function and that side you would have an increasing function. So were you able to understand? If you have a doubt, because we sort of missed a trick, we had forgotten we had to multiply x. So that's why there may be a bit of confusion. If you have confusion, you just ask me now. Okay, good. Last few questions before we go to integration. So number 9, local maxima I did not get. Okay. So what do you do for finding a local minima and maxima? You only do a second derivative test, right? Or you do, I did this once in the beginning of the class today also. So when you have a positive, this is your derivative function, right? Derivative you understood, right? This is your derivative. Your derivative looks like this. So if your derivative is changing sign to positive, from positive to negative, what does a positive derivative mean, Ravi? Positive derivative means an increasing function, right? And a negative derivative means a decreasing function. So if you on your left you have increasing, on your right left you have increasing, on your right you have decreasing, what does it mean? This is a maximum, right? Understood? So if you are changing sign from positive to negative, it means you are having a maxima. If you are changing from negative to positive, it's a minima. Understood? I hope it is clear. Still no response yet. Okay. Like local is because everything is local. We don't know about the idea global, any global idea. We have seen wherever derivatives are set to 0, they are called local extremas. Because globally anything can happen. A global minima may not exist ever. Like in this case, a function is always going to increase. Your function would have plus infinity as your local maxima and your negative infinity as local minima. As your global maxima and minima, not local. So next question, this one. So what is the shortest distance between this curve? So any idea what do you do to find shortest distance between curves? What would you do? So let's see, if you have two curves like this, your shortest distance would clearly be when the tangents are parallel. Or right, or if they're not cutting one another, perpendicular distance, or your normal distance is perpendicular, right? Normal is common. So if you have a common normal, you would have the minimum distance. Agreed? Between these two you would not have a minimum distance.
Yes, sir. Agreed.
So if your normal is common and your tangents are parallel, you would have a shortest distance. So for this case it's a easy problem, but in many cases it may not be trivial. Let's see. So x square plus y square minus, so I'm just dividing my 9 all over. So I get 10 is 3, 10 by 3y plus 16 by 9 is equal to 0, right? Which is x square plus y minus 5 by 3 square equal to 1, right?
Yes, sir.
So this is equal to y square minus 10y by 3 plus 25 by 9. If you subtract this, you get 16 by 9. You get back the original equation. So this is an equation of a, what is that equation of? X square plus y square is equal to r square. What is an equation of?
Circle.
Yes. So this is why you see the question becomes easy. For circle, any line joining the center is a perpendicular, right? So you have 5 by 3 and 1, right? This is 0 comma 5 by 3. Agreed? This is the circle it will look like. And you have y square is equal to x cube. So x cube curve is like this. And I told if it is y, if you are taking square on the y side, you take reflection about y axis. Remember that? So even for y negative, you would have the same value. So this is your y square is equal to x cube. Agreed? So this something like this will be your, yeah, go ahead. Doubt?
Yes, sir, agreed.
So x0 say y0 is the point where the distance is minimum. Agreed? So I will try to find the tangent or the normal. How do I find that? Be careful. These type of questions you must be very familiar with, because this is where you test your geometry calculus together. See, so one equation, right? So this lines 1 m from the line, what is that? 5 by 3 minus y naught by 0 minus x naught. Agreed? 5 by 3 minus y naught by x naught, or y minus 5 by 3 by x naught. Is it right? This is the slope of this line.
Yes, sir.
Yes. So I need another equation to get the slope of this line. From where will I get it?
Differentiate y square is equals to
Very
x cube.
good. This is what I wanted to. So I'll get dy dx is equal to 3x square. So I know dy dx at x0 y0 is equal to 3x naught square by 2 y naught square. Agreed? Or what is the slope of the normal? Normal into dy dx is minus 1. They are perpendicular lines, dy dx.
Yes, sir.
And normal. So your normal slope is minus 2y square by 3x naught square. Agreed?
Sir, 2y
Y, right.
naught will come.
No square will come. Right? This is correct, right? Yes, I think it is correct. So 2 minus 2y naught by 3x square. And this will be equated to y naught minus 3 by 5 by x naught, right? This has to be equal. Agreed?
Yes, sir.
So now what will I do? This is also a point on this curve, right? So I can put the value of y as some x, right? So y is x to the power 3 by 2
Yes, sir.
by x naught squared. You have x naught to the power 3 by 2 minus 5 by 3. So if I multiply it that side, so I get x naught to the power 3 by 2 plus x naught to the power 5 by 2 minus 5 by 3 x naught, right, is equal to 0. Is this correct? I think so. I multiplied this here, so I get this. Okay, so far so good. So I take x naught common, I get 2 x naught to the power 3 by 2 plus x naught to the power half, right, minus 5 by 3. I think there is some problem here. So yeah, there's 3 here. I forgot to write the 3. You did not tell me this time. Right? There was a 3, right? Am I audible?
Yes, sir.
Are you people sleepy? So there's a 3, right? 3 I forgot to multiply. So if x not equal to 0, so you can see at x naught also you could this is there. You can check for x naught equal to 0 as well. X naught equal to 0 is a solution and x naught equal to 1 is a solution, right? X naught equal to 1 comma x naught equal to 0. Agreed? This is not a solution because it's not differentiable at x equal to 0. We have seen that it's not a function, so it's not differentiable at this function is at this point, right? Yes. Yeah, 3 was there, so correct. So your y naught is also 0 or 1. X is 0, 1, so y naught is also 1 from this equation. Agreed?
Yes, sir.
So what is the distance between the center and this? So distance is root over of 5 by 3 minus 1 squared plus 1 squared, right? Agreed? This turns out to be 1 comma 1. So this is the very nice problem, I think. If you understood, if you have a doubt, you just go ahead. So this is your 3, 2, 4 and you have 3 square is 9. So you have 13, root 13 by 3. So is this the distance between the curve, minimum distance between the curve at 2 curves?
Yes, sir.
No. See, you are
No, sir.
not paying attention.
Minus 1.
This is the distance,
sir,
right?
we have to minus the radius.
Minus 1.
Yes. So the distance from radius to x naught is this. So from surface to this is d surface to x0 y0 is equal to root 13 by 3 minus 1. So this is why I was asking. If you remember, if you are paying attention, you shouldn't have said yes. Okay, so maybe we'll not go into, no, maybe we'll go, no problem. Let's have one more question, a few more small questions, and we'll be done with this. Okay. So find the equation of normal at the point where it meets y is equal to 4x. Yes. It's not continuous at x is equal to 0, but at x equal to 1 comma 1 it is continuous. That's what I meant. So number 10, let's do. It's a short question. So what do I do for number 10?
First, we will find the intersection point.
Nice. So we'll find the intersection between this curve and this curve. So it tells that where it's just the normal where you'll just find the dy dx. So it's an easy question. So I could have left it for you, but there's a trick here. Finding the intersection would not be easy just by putting y equal to 4x because you have cubic equations. Instead, you can do something that you learned in class 11 and 12, coordinate geometry. So this is y square equal to 4x, not y is equal to 4x. Y equal to 4x is very simple. I think I erased y square. So y square equal to 4x. So y square equal to 4x. Do you remember how can you parameterize y square equal to 4x? Does anyone know?
2 cos theta 2 sin theta.
No.
T square 2t.
Yeah. So t square comma 2at. So if you have a graph like y square is equal to a 4ax, so you have, if you t is a parameter on the curve, you can have, see, I'll put t value, right? I'll put x is equal to 2at. In our case, a is 1, right? So this is the equation of a parabola set with this focus at a. I think you remember that. So you get, so if I put x is equal to 2t, right? So what do I get at y? I get, and if I put y is equal to t, so is it matching both sides? Y square is equal to t square. No, what am I doing wrong? No, it's okay only. Y is equal to 2t, right? Y is equal to 2t and x is equal to t square. So I'm getting the LHS is equal to 2t whole square, which is 4t square, and RHS is equal to 4 comma t square. So I'm getting LHS equal to RHS. Agreed?
Yes, sir.
Yeah. So somebody said Ravi is saying a equal to 1. Correct. So a point will be, any point on this parabola can be written as t square comma 2t. Agreed? Now why is this interesting? Because we have seen parametric differentiations, right? We saw, right? And a curve is something like this. At this point I want a tangent to this or a normal to this. So what is the derivative? dy dt is 2, right? And dx dt is 2t. Agreed? From this?
Yes, sir. Yes, sir.
So what is dx dy? Or minus dx dy is the normal, right? Dy dx into normal has to be equal to minus 1 since they are perpendicular. So this is the normal curve. So minus dx dy is
Minus t.
minus t, right? So you are told to find the equation of the normal at the point where it matches the curve. So dy dx is y is 2, x is t square. Correct. Good. Now I'll just put this value here in this equation to get value of t, right? So x is t square. So t to the power 6 plus 8t square or 8t cube is equal to 8 or 16 t cube, right? Is it right? I just put x is equal to so t square into 2t is 2t cube. So right hand side is correct. Right, left hand side is y cube. Y cube is 2t cube. Yes. So t, say not equal, t is not differentiable at equal to 0. T is not equal to 0 since it is not differentiable. Not differentiable at t equal to 0. Agreed? This is point of not differentiable. So I'll get t cube plus 8 or 16 t plus 8 is equal to 0. Right? Good. So for what values of t do I write this as?
Sir, it's t cube. We can minus directly.
Yeah, it's t cube, na?
16
T
t
cube
cube.
is equals
yeah.
to 8.
Sorry, I'm wrong calculation. Even if I not equal to 0, then also, right? So t to the power 3 is equal to 8, right? I'm writing why did I think? Yeah. So t is 2, right? Agreed?
Yes, sir.
So your x comma y is 4 comma
4, 4.
right. So your line of the tangent of your normal would be y minus 4 is equal to minus t
Minus t
into x minus 4 or
x
minus
minus 2.
is equal to 2. So y minus 4 is equal to minus 2x minus 4. So we'll do the last question of differentiation for this year hopefully. So this is for what values of a does they intersect at right angle. This is also a very nice question. So how do you find if a curve intersects at right angle or not?
Product of slopes is equal to -1.
Product of the tangents.
Yes, sir. Product of the slopes.
Slopes, yeah. Product of the slope of the tangents. See, intersecting at right angle means we have always approximated curves by lines. That's all we do. We know only linear things. Calculus is making everything linear. Right? I think you have understood that now, by now. So, this is, if they intersect at right angles, your tangents must intersect at right angle. So T1, T2. So T1 into T2 will have to be -1, and also at this point both the curves must satisfy the equations. Agreed? Right?
Yes, sir.
Yes, sir.
This is an ellipse for your kind of like information. So, but anyways, we will not require that. So let's take the derivative. So we'll have 2x by a square plus, so I'll just put the values directly, by 4. You must remember that I'm putting the values x0, y0 after I'm doing differentiation. I'm not doing just like that. dy dx is equal to 0, or you have dy dx is equal to 2a square.
16 by 3.
Okay.
Sir, I was doing the next curve. sir.
Okay, it's okay. Yeah, you can go ahead. So it's minus 2 x naught square x naught by a squared into, it's 4 by y naught. Negative, right? This is correct. This is the first one. The second one, I took this by taking derivative on both sides. This one, again, as Hedvi was pointing out, so I'm differentiating this. dy dx is equal to 16, right? 16 by 3y square, right?
Yes, sir.
So the product has to be -1, agreed? 4x naught by a square into y naught into 16 by 3y naught square has to be -1, agreed? So I have 64 x naught by y naught cube is equal,
3a square.
right? Agreed? Did you say this?
Yes, sir.
So you see, what can we use now? Now do you agree that x naught and y naught is on both curves? Right? So this equation must be satisfied, right? Y naught cube is equal to 16x, right?
Yes, sir.
So you see, I will put put this, or you can just see that this is nothing but 4, right? Or you can just put it if you want to just visually see x naught by 316 x naught 4. This is plus minus root over of 4 by 3 or 2 by root 3. Understood?
Yes, sir.
Good. So now we have come to end of problems on differentiation. Today I will just give you a warm up. I have a couple of questions on integration. I see that the next sessions we would not do indefinite integration directly, but I want you to give you some flavor. We would do variable changes and so on, but doing integration like differentiation is not trivial. So Ravi, you may have unmuted, but you're not audible. So what I'm trying to do is, integration is not trivial. Why? Because you need to do a inverse differentiation. We'll be soon seeing why is the problem. So you see, if you have a dy dx, ddx of fx, so you can also see the derivative of fx plus c is also g of x, right? Agreed? Any constant that is independent of x, because ddx of c is 0. Therefore, to inverse a differentiation, so what I do, I put this side. So I do df is equal to gx dx, and to get f I integrate both sides. This is called an integration. So integration is, we will see, is an addition of small parts. So this is an idea. So we will not go to why it is an addition of small parts now, but we will think of this as a inverse differentiation problem. Agreed? We will see that in the next class, just for some computing, getting the feel of things. Did you understand what I'm doing?
Yes, sir.
Yes, sir.
So what I was doing is, if you take a differentiation of fx plus c, you will get gx. So if you integrate g of x, it's just like if you multiply a with b and you want to invert it, you need to divide by the same number, right? It's just like that. It's just an inverse operation for the time being. We'll see the geometric and actual meaning of integration later. So if I want to get back f of x, I will integrate this and get it back. So I have listed down a few formulae for indefinite. You can look at these, but these are not important because these formulae you will only remember. So you can try and see why is this true. How will you do that? You will take the derivative of the right hand side. Take derivative of RHS and try to land in LHS, right? So for now that is enough. Agreed? Understood? So we will take the derivative of the right hand side function for the time being, and that will be the left hand side function, means whatever is inside. So but let's solve a question and see how to do integration in general. So x sine of 4x square plus 7 dx. So it is not in the table, right? The table I have given you, it's not there. Agreed? Do you see? Is it there in the table? So we will only use this table for the time being. I have x to the power n sin x cos x sec tan x sec x x square plus a square x square minus a square root over x square minus x square. I don't have x square into this. So you will not have everything. You will only have 10 formulae, and you will have to bring it to those 10 formulae. Understood?
Yes, sir.
So in this case, I'll give you one way to do it. So this is by construction. T of 4x square plus 7. What is it?
8x.
It is 8 x dx, right?
Yes, sir.
I'm taking a differential of a function. That's it. A small differential, how is it changing? So this is known as or you can, this is a way of writing differentials, or you can just take ddx and think of this way. But I like this method because you're taking how a function changes with small changes in x, like we did approximation today. Remember, that's why I like this notation, and it will be useful in integration a lot. Agreed? So now, do you see that if I replace this, so if I do x dx as d of 4x square plus 7 by 8, now I have a formula that I know. Do you agree? Now this formula is in the
Yes,
table.
sir.
This formula is in the table, right? See, sin s ka integration is cos x. I am trying to match these two, so that these two match totally, and now I can put 1 by 8 minus cos of 4x square plus 7 plus c. Agreed?
Yes, sir.
Another way is, this is a good way to do it. You can, I always, when questions are small, especially in many places and physics and all, you can do this, or you can do something like this. 4x square plus 7 is some t. This is known as Weiss substitution. I'm essentially doing substitution, but I'm doing substitution in line. That's the idea. So if you do that, you would see you get 8x dx is equal to dt, right? Now x dx is 1 by 8 dt, and I will replace the original equation. So x dx will be replaced by dt, and sine of 4x square plus 7 will be replaced by t. Agreed? So you will get minus cos t plus c, right? And then you put the value of t back. Okay? Change in dx, how does it affect? No, I am taking, do you see I am taking a derivative of this function d. I am taking a differential or derivative of this function. So if I take a derivative with respect to x, so you will see that if you think there is no variable in the denominator, so there is only one variable that you have, that is x. So if I take a derivative by chain rule, I will differentiate 4x plus 7 and then I will differentiate x. That's the idea. Understood? So I'm trying to replace dx by this form so that your arguments, function arguments, become same, like in this case. So we'll stop here. I will do this question in the beginning of the next class. We will do it next class. It will require some time. Next day. We've already overshooted. So if you have, yes, this is smaller than substitution methods, because once you are getting the practice of things, you would be able to do like this instantly. So you would know that d of some x to the power n is n plus 1 dx. So you can directly manipulate d inside. You can change d x function to any function, and you can see how this changes on the outer side. So if you want to do this, I will give you a homework. This is also very simple, so you can try. So I forgot to mention one more formula. 1 by x dx is log x plus c. So my question would be log of sin x cos x dx. Try to do this, you will understand how to do. Not this, sorry. Or you can do two more questions. Let me just think. Okay, let's see. Log of x by x. This is one integration you can do. This is one homework. Second homework would be log of sin x into tan x. Or tan x, is it cot x into log sin x. Try these two questions. Yeah, try these two questions and we will catch up next day. Okay? This will give you an idea of how to do things. The way you just, if you want to replay, you just replay the part which I did change dx and try to solve these two questions. So that's enough. That's enough for today. Let's stop here and we'll meet tomorrow and like next Saturday, right?
Thank you, sir.
Thank you, sir.
And if you have any doubt, like I told last day, please share it with me via email.
Okay, sir.
Sure. So thank you. So we'll see you
Thank
next
you, sir.
Saturday. Next Friday. Bye.